Afternoon all. Yep. So my name is James Mitchell and I work for Sledgehammer Games in Melbourne. So welcome to my talk on expert level debugging. When preparing this talk, I knew I didn't have enough time to cram in everything that I wanted to. So I started thinking back at seemingly impossible bugs which I have seen. One class of bugs stood out above the rest, and those are ones which required reassembling corrupted call stacks. Let's say you've just shipped a game and it's out in the wild and you start looking at crash dumps coming from production and suddenly you spot this. So, assuming that you've got debug symbols loaded correctly, then we possibly have some stack memory that's corrupted that's preventing the debugger from showing us a meaningful call stack. I'm going to show you how to work with such a crash and reassemble a call stack from it. So a small disclaimer before I get too far into it. The examples in this talk will be using C++ inside of Visual Studio, running Windows 10 on x86-64 architecture. Other platforms, debuggers and languages will differ slightly. Just to get a quick sort of gauge of the audience, how many people in this room are using C++? Can you put your hands up? Right. How many are using C#? So it's about the same, 50-50. So this is primarily going to be a lot of C++ code, but still good knowledge to have. So the agenda for this talk, I'll give a quick little introduction to x86-64 assembly, and then the rest of the talk will be a demo with call stack corruption. So let's dive into some assembly. So within assembly there is registers. These are the equivalent of variables within higher level languages. For x86-64, there is 16 64-bit general purpose registers. These are the RAX, RBX, etc. They're commonly used for integer and pointer operations. There's also 16 128-bit SSE registers. These are the XMM0 through to XMM15. They're commonly used for floating point and SIMD operations. There's also an instruction pointer, which is the RIP register. And there's also calling conventions that typically get defined for how these registers are used, along with how the stack is used. For Windows, the integer registers at least get stored into the registers RCX, RDX, R8, R9, and then the rest of the arguments will be placed onto the stack. The return value gets stored in the RAX register, and then there's a set of volatile and non-volatile registers. The volatile registers can be changed within a function and don't need to be restored back to their initial value when a function returns, where the non-volatile ones, those need to be restored back to their initial value. So additionally, with the general purpose registers, there's the standard 64-bit way of accessing those registers. For the RAX register, you just use RAX. With the R prefix, if you want to access the lower 32 bits, you use EAX, so that's with the E prefix. And then if you want to access the lower 16 bits, it's AX. And then if you wanted to access the upper and lower parts of that lower 16 bits, then it's AL and AH, so the lower and higher bits of that 16 bits. For the newer registers that were introduced in 64-bit, which is the R15 through to the R8 through R15, they're slightly different, where there's a different suffix that's used to access those lower bits. So for the R8 here, we had a D prefix for a D suffix for the D word, which is the lower 32 bits, W for word for the lower 16 bits, and then B for byte for the lower 8 bits. We also have instructions that are used within assembly. Instructions are made up of an operation and then a set of operands. Operations are things like call, return, add, subtract, multiply, and then operands are either registers, immediate values, or memory addresses. Within this talk, I'll be using the Intel assembly syntax. This is my preferred syntax, and it's also the same one that's used within Visual Studio. With the Intel assembly syntax, the destination operand is stored on the leftmost operand, and the rest of the operands typically make up the source. There's also a stack. The stack is used to store local variables and arguments which cannot be stored in registers. It'll also store the return addresses from function for where a function should return to. The stack gets tracked via the RSP register. This is the stack pointer. It points to the very top of the stack. It'll grow from a higher address towards a lower address. Here's a small little example with a push and a pop instruction, where if we push 10 in hex onto the stack, the RSP pointer moves up, and then the value 10 is added where it previously was. And then if we do a pop, it'll do the opposite. It'll pop that value off the stack, and it'll store it within the RAX register. One thing to note here is that the data that was on the stack didn't actually change when we popped that back off. It still has the 10 there. This 10, if you're using a programming language like C or C++ and you don't initialize a local variable, this might be the data that you end up seeing, which is commonly called garbage. Now let's take a look at how function calls work. So when a function is called, typically at the start of a function, there'll be a prologue. The prologue reserves stack memory for the current function and also will save any non-volatile registers to be restored at the end. These will be restored by the epilogue, and it'll also restore the stack pointer back to its initial state. Here's a small example where we're pushing on the non-volatile register RBX, and then we're subtracting 24 in hex from the stack, and then at the end we readjust that stack back down 24, and then we pop that RBX register on before we return. Now I'll take a look at with stack variables, those are typically accessed with an offset from the current stack pointer. Here's an example where we're doing a move instruction of 10 in hex into an offset of RSP plus 4. So the RSP is defining where the sort of top of our current function frame is, and then we're doing an offset of 4 to store a variable there. This typically, for this function, it would have done a subtract of some number greater than 4 to reserve that space. Not all variables will actually live on the stack. Some will exist within registers, or they might have been optimized out completely. And then depending on compile flags, there may also be a stack frame base pointer, which is typically called RBP. And it might be used to calculate the address of local variables instead of using the RSP. Additionally, if the debugger has symbols that it can access, it might end up showing variable names here instead of just the offsets from RSP or RBP. Such as this, where it's showing the my var instead of the offset from RSP. They both mean the same thing, it's just a slightly different way of viewing it. So now let's take a little bit of a look at the call and return functions, the call and return instructions. The call instruction, what it'll do is it'll push the address of the next instruction onto the stack. In this case, it's going to be the instruction that has the move RAX 10 in hex, and then it will jump to the function that's being called. And for this, it's going to jump into example 2. So let's take a look at what that does. So the stack pointer is moved up to push that value on. It's put on the stack there, the 7F with a bunch of zeros and a 4. And then the return instruction, what it does is it will pop the address that was placed on there for the return, for where it should return to, and then it will jump to that address. So it does the exact same thing. Again, just like the previous examples, the values are still left there in memory on the stack. We've just moved that stack pointer when it's popped that back off. For Windows 64-bit, there's an ABI, an application binary interface that gets defined for how the stack should be used. And for it, the stack should always be aligned to 16-byte boundaries. And there's also a 32-byte reserved parameter stack home area just after the return address. It gets controlled by the callee and it can change anything within there. There's more resources online which go into better detail on different ABIs for different operating systems, and also much more detail on assembly, but this is just the quickest little rundown that I could try and fit into the talk for those that have limited idea on how assembly works. So now let's start getting into the meat of this talk, the demo and some call stack corruption. So this is the function that I'll be primarily using for corrupting the stack. It's a function that called zeroNumber that takes in an index, and using that index it'll set a number within an array of 4 elements to 0, and then it will loop through that array, printing out each of those numbers. So let's take a little bit of a look at the disassembly for that function. You don't need to understand every line of the assembly here, but I'll give a quick little rundown. So first up, we've got the initialization of the numbers array. This gets stored in the stack at RSP plus 20 in hex, as you can see by the last line that's highlighted. Then we have the setting of the value to 0 within that array. And then we have the loop through the numbers array. And finally, we've got the printing out of each of those numbers within the array. And then we've got a little thing here that I haven't quite discussed yet, which is a stack cookie that's used to detect if a buffer overrun or a buffer overflow occurs. This is where this places a number onto the stack just after all of the data for the current stack frame. In this case, it's placing it at RSP plus 30, so that's just past where the numbers array will be placed. And it checks whether that number is changed at the end of the function. And if that number has changed, then typically it'll crash the program. If you're running it within a debugger, it'll stop it. It'll tell you that some buffer overruns occurred. However, this is only placing in a 64-bit number onto that stack. So if you start writing anything that's past that 64-bit number, it's not going to end up checking that. And that's where we could end up corrupting further things within the stack. So it works really well if you've got a buffer that overflows and you're doing it continuously. But if you start accessing things randomly inside of that array, that's when this won't pick things up. And then finally, we've got the prologue and epilogue here, where it's pushing on that non-volatile RBX, and then it's reserving 40 bytes in hex. So this is enough for that numbers array. It's enough for the home area, and a bunch of other things. So let's take a little bit of a look at how that stack is laid out. So before I get too deep into this, I'm using a lot of offsets on the stack offset here. You can see where I'm doing 0, then +8, then +10, +18 hex. This is typically the way in which I'll view a stack. I view it in 64-bit increments, as that's, well, on a 64-bit machine, that's typically the way it'll be accessed. So it's useful to learn how to count in these. So the way in which I'd sort of view it is that you start from 0, then 8, then it's going to be 10, then 18, then 20, then 28. So you're just sort of changing that 8 back and forth and incrementing the number at the start. So the stack layout for this function is the home array is placed just below the stack pointer. And then we've got the numbers array after that, starting at 20 in hex, going all the way up until 30 in hex, followed by that security cookie detect buffer overflows. And then there's some padding to ensure that everything is aligned to the 16-byte boundaries. Then we've got a saved RBX register. And then we have the return address that returns back out for where this function was called from where it should return to. So let's take a little bit of a look at what might happen if we start storing values in values above 3 within this numbers array. So if we start storing stuff within 4 and 5, then we start overriding that stack cookie. And this is where hopefully the debugger or the program will crash, and it'll tell you that that's occurred and you can go in and fix it. If we start changing numbers 6 and 7, we've overwritten the padding. This probably won't show up anywhere, shouldn't have any real impact at all. We're just changing random bytes of memory. If we start changing numbers 8 and 9, then what we're doing is we're overriding that saved RBX register. So this could end up with extra side effects within the function that called zeroNumber. Because when it returns, it's expecting the RBX register to be unchanged. But now we're going to change it to something else, so it might display other side effects within the function that called this, or possibly even the function that called that. And then finally, if we change numbers 10 or 11, then we're changing that return address. So then the function might end up returning into some other completely different place. In this case, we're setting the number to 0, so it's probably not a real memory address that can start executing on. So that's it for the stack layout for this function and what could happen if we start storing random values a little bit further out into the numbers array. So now let's get into a live demo. But instead this time, we'll pray to the demo gods that it actually crashes. I've just got to switch back to duplicating. So here's that same 0 number function. I've added in here a no inline just to ensure that the optimizer doesn't end up inlining all these functions. We've got no call stack to actually look at. So I'll start from main and sort of show how this function's working. So first off, I iterate through numbers from 1 through to 10, and I call func1, and I pass in the argument for the iteration number that's currently going through. Then within func1, I'm taking that argument just as a const reference, and I add 10 to that number, and I call func2. I also return these arguments, I do, and then func2 doing the same thing but adding 100 within hex. Func3, same thing, add 1,000, calls func4, and then func4, what it's doing is it's asking the user to pick a number, and then it'll call that 0 number function, and it will instead of just taking that number, it'll output it as out to std out, so then we can see it within the console. So let's run this example and start trying some different numbers. So let's try the number 1. It's a valid number. We shouldn't expect anything bad to happen with that. It's showing us the numbers 0, 1, 2, 0, 1, 0, 3, 4, if I can actually read. And then the args that it's showing is 4 ones. Now if I try 2, it's showing as 1, 2, 0, and then 4. Try 3, we'll change that last one of 1, 2, 3, and then 0. Now if we start changing 4, oh, looks like it's crashed, saying that the stack cookie instrumentation code has detected a stack-based buffer overrun. This is what we want to happen if we start doing something bad. And it's given us, we've got the full call stack here for this, so we can start debugging it and digging deeper. But let's start trying some other numbers that aren't quite as easy to be picked up. So what was that number that we were 4? 5's going to be that same sort of stack cookie. Let's try 6. 6 doesn't give us anything, that's in the padding. We'll try 7, that's still within the padding. How about we try 8? We've got a slight bit of change in behavior there. Now it's saying that arg is 0, which isn't what we expected. So that's probably happening because we're changing that RBX register that was saved onto the stack. And now the function that called that, it was expecting RBX, which is probably where it stored this number in it, the number that it was taking as an argument. And it's accessing it, and we've zeroed that out, so it's gone. How about if we try 9? Well, still works, it's still giving us that, so it's probably only the lower bits that were sort of causing that RBX register to be used. This is just an integer that we're passing in. Now let's try 10. And now we've properly crashed. So access violation, executing location 7FF6, bunch of zeros, a call stack there that's not giving us anything. What are we going to do? So from earlier, we might recall that the return addresses for each of those functions were pushed onto the stack, and that stack was pointed to by the RSP register. So let's open a memory window and see if we can try and find some things on the stack. So just up here, I'm just going to open a memory window up, expand that a little bit further. So within the address here, I can access the stack pointer just by putting in a $sign and then RSP for the stack register. I'll close this, just get it out of the way. And here we can see all the bytes that make up that stack, or at least where the stack currently is. But this is a little bit harder for us to read, so what we'll do is we'll view it as an 8-byte integer, so I'm just right-clicking here. So it's just an 8-byte integer, so it's giving us a little bit more useful values. You can see at 1115, we know that was sort of related to what we were working on. We can see this looks like it could be some memory address to an instruction or something. So let's try and take a look and see whether that is an instruction, because we know that there's going to be return addresses on that stack. So what I'll do is I'll click View Disassembly here, and at the top of this disassembly window, we can paste in addresses. So I'll copy this address just here, and I'll paste it in. Unfortunately, because this is just a bunch of numbers within that address, I either need to prefix it with 0x to make it get treated as an integer, or add a h to the end. So I'm just throwing a h on the end of that. And you can see here that the address where I just typed that in is changed to an actual name. So this is telling us that that address is pointing to somewhere within RTL set last win32 error. That's not very useful for us trying to solve this issue if it's just popped up in production. Let's keep going through these next things. Let's see where this takes us. We've got to add that H to the end. Bunch of question marks. Let's keep going. Let's try this one. Question marks, that's 115. Let's try this one. Oh, we've found something that relates to what we were working on. We found a func3 here, and it's put us just at the return address of what looks like func4. So possibly func4 was within there. We could keep repeating this, sort of going through each of these numbers on the stack here, but that's probably going to get quite time consuming. I stumbled a little bit on my words. So there's a slightly easier way for us to do that. And also when you start getting bigger stack frames, which typically happens if you're storing more than just a standard integer on it like we're doing, then you don't want to be going through thousands of numbers to try and search through this. So what I can do is I can use the watches window down here, and I can cast the stack pointer to a void pointer. And then I can treat that as an array, and I'll treat it as an array of 128 elements. Let's just enlarge this a little bit as we'll dig into that. I might close this memory window down as I'm not currently using it. So now that I've treated that as an actual array, what Visual Studio has kindly done for us is started resolving symbols, because they're a bunch of void pointers. So if we scroll through this, we can see that we've got what looks like main, what looks like func1, func2, func3. These are all those return addresses. So we've got a call stack. Done. That's all we wanted, isn't it? We can work out where this was expecting to go just by copying the addresses, paste them in here, and just seeing the return address. So it was in func4 probably where it was expecting to go. What we can do is try and validate whether that really was, whether the rest of this data here that's on the stack, because we're expecting another return value that this was going into, whether that was potentially from func4. So let's go to the disassembly for func4. Again, just copying this address, pasting it in here. And I can see that this is taking us to the start of func4. So what I want to do is try and work out how big the stack frame is for function 4. And then we can try and establish whether all of this is function 4, whether some of it is, whether what likelihood it is that we were returning back into func4. So first off, we look at the start of func4. What we're doing is there's a push RBX, so that's probably this value here that's just highlighted. And then we're doing a subtract of 30 in hex. So each of these numbers here is going to be the equivalent of 8 in hex. And that's where when I mentioned that counting before. So if we count from this, we've got, this is going to be 8 in hex, 10 in hex, 18 in hex, 20 in hex, 28 in hex, and 30 in hex. That's that stack frame that we were looking at before. So that likely means that it was returned from, that was a function that was returning back into func4. So we know that we've got func1, func2, func3, and func4. So we've got most of that call stack established. However, this is quite a naive example. It typically won't be that easy to spot a bunch of these in here. So I prepared earlier, let's get rid of this one, prepared earlier a little function down here, which you might have spotted commented out earlier, func A. And what I do in that is I call a bunch of other different functions. I have a slightly different stack layout. Now let's see what happens if we start doing that same thing. So I'm going to put an 11 in this time. So again, we've got no call stack here that it's showing. We start expanding and trying that little trick that I just showed you. Let's get rid of this. Now let's start back from main. Try and work out what functions we might have called. So we went from main, then we went to func1, func A. Func1 didn't call func A. Func2, func B, func3. Oh, I've accidentally scrolled. Func3, then func C. So the whole bunch of different things that really we didn't call at all there. So the way in which to try and establish what was that actual proper call stack is to start from a function that we know is probably going to be on the stack. And in this case, we know that main's going to be on the call stack. Typically, if you're running a bunch of threads and you're doing this on a thread, you might have a sort of thread thunk there that exists, and you start from that function. And then you work your way down trying to establish what called what. So in here, we can go back to view disassembly. You can paste in that same address that we've just copied for, actually we copied func1 there. We want to start from main, because main is the one that we know. So we paste in the one from main, and it's taken us to this address here. And just above that, we can see that it's func1 that it was calling. So that means that it's expecting to return from func1. So func1 should be the function that was called. Repeat the same thing. Grab the address from func1 here for where it's returning. Paste it in, and then we can scroll up because it's put us a little bit above there, and it was into func2. And we can keep repeating these same steps. We can. However, what about if here we had func2 appearing twice? How do we know which one to actually look at? That's where we've got to work from these functions and look at that stack frame size like we calculated earlier. So here we can grab that func2, and again we'll look at how big that stack frame is to work out if it was the one that was returning back into func1. So this is assuming that func A here also said func2. So we wanted to work out which one it was. So we can calculate the stack frame size for this again with that push RBX. So we would expect that to be the push RBX there. Then we're going to push, then we're subtracting 20. So we've got to count up to 20. So 8 within hex, 10 within hex, 18 within hex, and 20 within hex. So this would have been the func2 that we would expect if both these were func2. So that sort of gives us a good approach for sort of digging into some of these. However, there is also situations where you might not get the full call stack here. So I'll show those examples. So what you might happen is a function call might end up getting turned into a tail call optimization. This is where instead of using those call and return instructions, what it might do is it might use a jump directly into the other function. So what I'm going to do here is change this func2 to not return any values. It's just a call through to func3. We slightly change the arguments a little bit. And now let's start looking at what appears on that stack. I'll try 11 again. Yep, we've crashed. I seem to crash a lot in this demo. I'll get rid of this value that I accidentally copied onto there. So now we'll ignore the A and B. We know they're not related to anything, but we can see here that we've got main, then we've got func1, then we've got func3. Func1 didn't call func3. So let's start following from func1, we know that it's going to be on there. Go to the disassembly, view for it, paste in the address. We can see that it called func2. So let's take a look at func2. And I'll just move that down. So this is all the code that exists for func2. So it's just adding on to ECX 100 in hex, and then it's doing a jump into func3. So that means that there's no return address that's going to end up pushed onto there. It just continues executing in func3. So that means that we should not be trying to look for a func2 on there and just start looking for a func3. So that's the tail call optimization things that you might run into in there. You also, I don't know whether you've noticed this occasionally within Visual Studio, just on the call stack when we have a valid call stack here, it might also be missing that func2 because it's doing the same sort of thing when it's trying to work out what the call stack is. It's just looking at that stack memory, looking at the addresses and trying to work out what's next. So that gives us sort of a little bit of a view into how to get that stack. How about if we wanted to access some local variables within this? So let's go back to that main function. And within main, we've got this one local variable here, iter_num, that we're iterating through. We wanted to try and work out what the value of it was at that point in time. It's looks like here we've got a let equal to instruction, which just, it does a math calculation to sort of store a number. It doesn't actually, it's a load effective address actually, not let equal to. It's got a number here that it's got on the stack. So we can't actually work out what that number is till we turn off symbols. So if I turn off symbols, that same line there is now changed to RSP plus 40. So the top of that main should be here where we've got the return address into main. So RSP plus 0 would be right here at just below that return from main, but we want to get down to plus 40. So again, we start doing these adding of 8 into this array. So we're starting here at 0, then 8, then 10, 18, 20, 28, 30, 38, 40. So this line here should be where that address is stored. You can see a 1 at the end of that, and we're on the first iteration through that iter_num. So that probably means that that's the actual number that was stored there for that value. Now how about if we want to try and work out what the arguments are for func1, which we should expect when we were looking at func1. We'll go into the code for func1. We will. I'll turn back on symbols. What I'll do is I'll copy the address for func1, go to it. So func1, with the ABI that was defined for x86-64 on Windows, the integer register, which is what this reference to arg is, it'll be stored within the RCX register. So what we need to do is try and follow where that RCX register, what happens to it within that stack frame. See if there's any way in which we can try and pull it back out from what was used. So here we've got the RCX that gets moved into the RBX register. This move it doesn't actually move and get rid of it, it's just a copy. And then what we've got just below that is we've got a move dword PTR here, so this is dereferencing that address from RCX and placing it into ECX. So ECX and RCX are both the same register here, so it's just overriding it. So the whole RCX register, it's gone. We can't look at that, but luckily it was saved in that RBX register. So let's try and follow and see what happens to it. So we keep going down, we go into func2. So func2 has potentially changed that RBX register or done something with it. So let's take a look at what func2 does with that. So this is where we've got to sort of keep following down that stack to work out what happens to some of those registers when we want to restore them. So this is just doing an add to ECX, and then it jumps to func3, so it's not doing anything with that, the RBX. So go to func3, So func3, what it does first off is it pushes the RBX onto the stack. So func3, that was called for, so func1 called func2, and then func2 jumped to func3. So the return address for that func1 would be immediately before we start executing func3. So that means that this address here that we don't do as a push right at the start of func3 should line up with the just after the return address from func1. So let's take this address, bring back up that memory window, paste it in, and it's taken us to this location here, where again we see a 1 because we're on that first iteration. So what we've done there is we're accessing that register that was saved, the non-volatile register that was saved. And we can keep repeating these same actions, going through each individual function, stepping our way through. So if we want to do the same for func4, so the argument here for func3, again, it's going to be in the RCX register. It's doing the same thing, moves it into EBX, and then it calls func4, it changes that ECX, so we couldn't recover it there. So we do the same thing. As you might sort of realize, that was another non-volatile register. Func4 does a push on that. So that means that if we find func3, because that was the function that called this, the value after that should be the argument that was passed into func3. So we've recovered it, that's a bunch of 1s. And we can keep repeating these steps and sort of try and resolve where things are. However, what I might show is another little trick that you can also use. This one will work primarily if you're live debugging and you start running into some of these, and that's actually going in and changing some registers to try and trick Visual Studio into giving us what we want. So we know from earlier, when we were looking at some of this call stack, is that this was func3. We don't see func4 on there, but we worked out from func3, the return address from it was a return address into func4. So we go to func4, and then we worked out from these, the push RBX and the subtraction from RSP, that this was the push RBX, that was the subtraction of 30, that this was the full stack frame for that stack. So that means that it's func4 that we're within, it does, and the address that it was expecting to return to, which should be on the stack just before this. So what I can do is I can go into here, if I go to $RSP again, so that's the top of the stack, but if I look at the number just before that, which is this one just here, then that number there should be the one that was expected to be the return address, and we can see just here on that call stack showing the exact same number for both those. So that's the reason why it's that return address was overwritten. And the return address for that we expect to be part of func4. So can we try and look through each of these call instructions and try and work out which one might have caused that? Luckily we know the code fairly well. We know it's probably going to be that call to 0. But if it was going to be the return here, then we would expect that this address here should be the same as this one. If it was going to be the call to 0 number, we expect it to be this one. And I don't know if there's any people that are looking at these two numbers in detail, but you might notice they're very similar. That the number here on the stack is exactly the same as the lower number of this. It is. We're just missing a few of those numbers. This number is that instruction pointer that I mentioned earlier. That was where when we popped that return address off and we jumped back to the return address, that gets stored in the RIP register, the instruction pointer. So what I can do is I can actually open up the registers window here and start putting in there. So we know that it's a return back from 0 number. We know that this is the return place that we're expecting to go to. So let's find the RIP register here. Let's start changing these register values. So if we change it to this same value that I've got highlighted, so what's that, 7FF7. Anyone see it change? We've got a call stack. We've got a proper call stack within C++ code again. We can switch back to source code and start mousing over some of these. I've got it viewed in hex. Let's turn off the hex view. You can see that the 0 number was 11. You can see that we've got arguments passed in here. I'll have to switch back to hex as those were the other arguments. See if I click hexadecimal, you can see it's got the bunch of ones that we expected on arg. We can keep walking back up and looking at each of those. So we can get all of those details back just by patching up some registers and getting it back into the state that we want. Unfortunately, that trick only really works when you've got a live debugging session to this. You can also do it if you've got a crash dump and you feel like jumping in with a hex editor and try and find the address that was bad and patch in what you want. I have done that before, but it is fairly daunting. You do often find several instances, so you end up change this one, try it, see whether it works, try another one. But typically you only might need to do that if you really need further details out of this, and getting in with the debugger and reassembling it from the disassembly gets a little bit harder, but it is possible to do it with a crash dump. So that's it for the live demo side of this. What I'll do, switch back. Is there any questions? I'll ask that people come up to the microphone here for any questions. Surely someone's got something.
Question I'm sure a lot of people have. Can I download this source code so I can run through it 100 times before it makes sense?
Yeah, there'll be a video online for all these recorded. I'll put up the source code for that, I will, and hopefully we can get a link or whatever added to that source code.
Thank you.
Yeah.
Thanks very much. So there's a lot of just stepping through manually and just repeating the process. How much work do you think it would be to turn this into a plugin so that you could have it do some more of the work so that you don't have to?
On my train ride down here, I was actually playing around with that idea. I was trying to see whether I could do the same. It is possible to do, but it's a matter of getting that level of accuracy which you need. If you do use other tools like, say, WinDebug, it actually makes it a little bit easier for doing this, but it's a much more complex tool to use. You get into that situation similar to Vim of how do I even exit out of it? It's lots of little commands to do different things. If you master WinDebug, then you're doing a pretty good job at debugging. But I figure a lot of people are in Visual Studio and you don't want to be, yep, I've got to learn WinDebug to solve this thing. It's like, just use the little trick here with just the watches window on that RSP. Typically you can make it out. You don't have too much interleaving, at least on the things that I've seen come from production that are similar to this. But I do want to play around with building a tool that makes it a little bit easier, at least in Visual Studio.
In a large function in assembly, how do I identify the point of return? It could be more than one even.
There typically is going to be multiple points of return within a function, at least anything that gets more complicated. But you don't need to know necessarily where the function returns. It's more you need to know the start of the function. The start of the function is always the same, and that's where you sort of can establish that the size of the stack from it. Unless, of course, you start doing things like allocate or one of these sort of things where you're allocating stack space dynamically, and then it becomes a lot more painful to work with. But yeah, You will, if you are browsing through the disassembly of a function and you do have symbols on, like within Visual Studio, it'll sort of show you the start of the function all the way to the end, but you might see multiple returns within there depending on the function itself.
When might you know to kind of cut your losses if the program is kind of too complex, or you're looking like a memory dump or something like that? Is there like anything that's like stands out to you that says like maybe this is getting too difficult, too much spaghetti to follow? Or
Yeah, so sometimes the approach that you might want to take to these is you might be able to just run address sanitizer or some other tools. You might just pick up whatever it is that was happening with that. But that only works if you've got reproduction steps.
Yeah.
You've got sort of something easy to play around with, or you might even just start manually tweaking things, turn stuff off and on until you find out where it was occurring.
Yeah.
There's multiple different approaches if you didn't want to dig into this lower level approach. But knowing when to cut your losses, that probably really depends on how are you seeing it all the time in production? Is it only a once off? And then that really sort of cost versus versus actual time that you need.
Cool.
Any other questions, or is that it? Did I put you all to sleep? No, he's awake.